Let me share my screen. Can you see my screen okay?
Yes.
Okay. Yeah, hello everybody. Welcome to another study session on zero knowledge proof. And this is a series that we study the latest, how to use the latest zero knowledge technique to build all kinds of applications on Bitcoin. So previously we have covered a lot of the basics, and today I'm just going to to kind of like put all the pieces together and show, we talk about separately how to build circuits, how to generate the proof, and we're going to see how this whole workflow is going to integrate in end-to-end user application. How does all the pieces fit together? So I'm going to use this example, as you can probably see on my screen. The example we released called zkBattleship. Basically, is for anybody who has heard about the very conventional game called Battleship, and we are putting it on the blockchain and using zero knowledge to prove whether a ship has been hit or not. And in this way, and also we are going to integrate, add a front end UI to it, so you can use some kind of wallet to interact with it and play with it. So for people, I think I'm going to post also the links in the show notes. So if you want to check out everything, including the tutorial and the source code, you can do so using the links here. So just curious, have you two heard about this game before or played with this game when you were young?
Of course.
Battleship?
This was a childhood favorite.
Okay, so all right, nice. So I don't have to give too much introduction on this, so we can focus on the zero knowledge part. So we released this course. Basically, it's a website called Learn Script, and we have previously we have another example called tic-tac-toe, and this one is more focused on the zero knowledge. How do you integrate zero knowledge with script, and how to then finally put a front end on top of it so users can play with it. So at the end, it will look like something like this. So it's going to be a browser. You can log in with some of the wallet that support this, so you can start playing with. I mean, in this case, because we want to make it easy, so you can play it locally. So you can just play with not with another human. So you are playing with a computer, but if you want to make it a production, you just swap out this part. So that's not a problem. And if you follow the link here, you can come here. There's I think it's a 5-step tutorial you can walk through, and then at the end you have become from pretty much zero knowledge about zero knowledge, and then you become I would say qualified ZK developer, which you can build a full suite zero knowledge app and hook it up with the front end, so other people can try it. Everything is runs in a browser, by the way. So in this example,
everything is what? I'm sorry.
Everything is runs in a browser.
So
there's no backend, no server needed for this example. And also all the zero knowledge, when you're generating the proof, is also in a browser. I think I'm going to cover in the last step pretty much. So I think because this side we have covered the basics before, so I pretty much just walk through this example to see how building a ZK app looks like. So again, for people who have not heard about this game, it's a classic guessing game. So basically you have two people sitting opposite to each other, and each one of them has a board, and they're going to place the fleet. You have some carrier, you have some cruiser, you have some destroyer or submarine. You put it in a fixed position on the board, and then the opponent is just going to guess. After you finish putting all this your fleet on the board, your opponent is going to guess the coordinate basically is a grid, right? So you're just going to fire at each coordinate, and then you are supposed to tell him whether it's a hit or miss. So the game keeps going on until one of the, one person's whole fleet gets sunk. So then that's the, then he lost. So we want to see, how to put this game on blockchain, but then that's a dilemma, right? Because if we put pretty much all the position of the fleet onto the blockchain, and then everybody can see, right? So you're not hiding. So if you're not hiding, I don't have to guess, where your fleet is at. So I can just simply just sink all your ships, I never miss one. So I can just keep shooting at where your fleet is at, right? So that's not going to work. But then if you don't put your fleet position on the blockchain, but then how is the smart contract or the miners going to check whether you're not ensure everybody's honest and not cheating, right? For example, I can say, hey, I file at this coordinate, I don't know, B7, right? You tell me whether it's hit, but I'm a trick you, right? I'm gonna say, oh, even though you hit my destroyer, I'm say I can lie to you, right? Oh, this is not a hit. So this is a perfect scenario. I hope to, this is a paradox, right? I just mentioned. If you put this onto the blockchain, everybody can see it. So you are not, you're not actually playing the game honestly. But if you're not, then you can cheat, right? So basically, there's a huge dilemma here. Hey, Zach, welcome.
Hello.
Thank you. Sorry.
Yeah, but just quick cap. So we are, previously we talked about all the different pieces, what kind of zero knowledge you can use, and how to generate proof and verify proof. So today I'm going to just put all the pieces together to see how we can build a full suite, ZK based app. So again, I think you have seen this example. I'm using the Battleship example here, and let's talk about the dilemma. If you put all the state on the blockchain, and then everybody can see it, so it's not good. So how to address this like a seeming paradox? The answer, of course, zero knowledge. Specifically, we talk about ZK snark. So how does this work then? We can go to the, a little bit into this is just the intro part section, and then we can go to, let's say, how do we design a ZK snark that can solve this paradox? I think I'm going to just jump right into chapter 2 because previously we already covered Socrates in detail. So how do we do this then? So, any kind of a zero knowledge ZK based app, first you have to design a circuit, right? So the circuit, one of the first things you have to do is decide what kind of inputs you're going to have and what's the output, right? So, and also in the inputs, you have to decide which one you're going to keep private. Okay, so for us, we do the same trick. So instead of putting all the plain text position on top of the Bitcoin blockchain, we put just a hash of it. So the hash, actually has two purposes. One is a placement, right? So it's a commitment. So once you put the ships on the board and you publish the hash, you cannot move the ships, right? Because then you're breaking the hash. Every time when you are checked whether it's hit or not, you're going to compare it with a hash. So you get a hash, that's an input, of course. And of course, the opponent's going to tell you what's the coordinate he's firing at, right? So we got an XY, the coordinate on the board. And of course, you got all the inputs for all the fleet of yours, right? So that's another information. But this information, this is information we want to keep private, right? Because we don't want the opponent to know the location of our ship. Does it make sense so far? This is inputs. So you have 3 inputs actually.
Yes, makes sense to me. Mm-hmm.
Okay, that's good. And the output, what the output of this circuit is, you're going to tell me the result. You know, whether I got a ship, you know, that's at this coordinate. So if you yes, it's a hit, right? Otherwise, it's a miss. And also, once we go through this ZK stack, you're going to also produce a proof, right? You're going to, hey, you're not telling me if it's a hit, it's a hit. You cannot tell me otherwise, right? Because otherwise the game cannot function. So here, you're gonna have the, you know, the strengths of both words. First of all, because you are only commit to the hash of the position, you're not disclosing the information. But also because you have to produce a proof, you cannot cheat in the game also. So that's how this using ZK Snark, you can solve the seeming paradox. You know, you can commit to a position without disclosing it, but also you cannot cheat because otherwise zero knowledge, the verifier would you can detect. Make sense so far?
Okay, so there's two outputs. There's whether or not the hit is true or false, and then the proof that verifies that the true or false that you're receiving is an actual valid true or false.
Yes, exactly. So this is the circuit. Okay, so I'm going to cover a little bit of a detail how you do this. So basically you have you know, of course, this is the interactive tutorial. That means, you know, we have the kind of like a skeleton or boilerplate for the circuit for you. And then you're going to fill in the remaining part. So you can also, for people who have not used this tutorial, you can also, if you really want to see if you get it right or wrong, you can also, you know, click this button and then show the hint. So now I'm not going to cover here. Basically, again, right, you can see this is the main circuit. So that's a Socrates DLCL language. You can write your circuiting. So basically you have all the flip position, right? Which is, you know, so here, so the basic data type is called a field. I mean, because it's in the end, it's going to be a field operation. Basically, it's you're going to do the modulus. So that's why it's called a field, because in math, is this set of numbers and the operation together is going to, you call it a field. Basically, you can think of almost like an integer, and it's about, I think it's about 250, a little bit shorter than 256. But for all purposes, you can think about this like, you know, just an integer, and it's a little bit shorter than 256 bits. So you can encode all the positions, right? So, you know, where the ship it is. So you can encode, you know, where it starts from, let's say XY coordinates, but also because the ship, right, you can be horizontal or you can be vertical. So you got another variable to see what's orientation. So together you can encode this, each ship in a state and put it in a field. Okay. So that's how you encode where the ship it is. Okay. So another thing I think I just want to mention a little bit here. So when we talk about hash here, right? So in reality, you can use all kind of hash as long as it's, you know, collision resistant, people cannot reverse it, then it's all possible. So you can use all kind of, let's say regular hashes, you know, SHA-256, SHA-3, you may even sometimes even MD5, right? But in our case, we are going to use the so-called MIMC hash, because, you know, this is so-called one of the so-called ZK friendly hash. So this hash actually, as I just said, it can be pretty much any hash, but for performance reasons, if you, let's say, use a SHA-256, you know, this is so-called not very ZK friendly. What does that mean? So when you use let's say SHA-256, the circuit, when you compile it, you know, the size is going to be huge. And if you use, let's say, some kind of like a ZK friendly hash, which one of them is called MIMC, is going to be much shorter. The circuit, the size of the circuit. Basically, the size of the circuit is, you know, you're going to impact how how long it's going to take you to generate the proof. Pretty much the smaller the circuit is, the more performant the whole thing, the ZK snark is.
Okay.
Does this make sense so far? So that's why we are not using, let's say, SHA-256 here. You can, but it's just not as performant.
So what you mean by friendly is the amount of time that it takes to process the hash or the algorithm, basically the SHA, so that's what you mean. It's just the runtime is how long it takes to process the transaction is what you're saying. That's what you mean by friendly.
Yes. So basically, think about once we have this code, right? This circuit in the high-level code Socrates, we're going to go through all the few steps, right? We need to set up, we need to compute the proof, right? So if the bigger the circuit, usually the longer it takes the more resources it takes. Both the memory and CPU is going to take you for the compile and also the proof generation. So you want that had to be as small as possible, because that's pretty much, it says that the complexity of the computation you're going to prove. So the more complex, the more resources going to take.
Right. That's
So
the big O notation, I think it's what it's referred to.
Yes, exactly. Yes. So the prover generate the prover time, the so-called prover time, is how long it does take for the prover to generate the proof. Usually, I think for most snark, it's called a quasi-linear, so it's n log n. You want to keep this n. N is pretty much how big is the size of the circuit. So because you can use any hash here, so SHA-256, it can be like tens of thousands of gates. And using this one, maybe you only have like a few hundred or 1,000, let's say. So you're reducing it by like 100 times, even though you're achieving pretty much the same thing. It's just a hash commitment. It doesn't matter which one it is. So I think you have MIMC, but you also have, all kinds of other stuff like a Poseidon or Rescue. But we can just choose a MIMC here. And this has also been implemented in our JavaScript code and also script code. So you can think about this as a library. This is just a ZK friendly hash.
Understood.
So this is a recurring theme. So whenever, in ZK, and that specific friendly hash. So usually, unless you are talking about some to be compatible with the existing system, let's say you want to hash some transaction or block to get the hash of the, let's say, transaction ID or block hash, because it's already using SHA-256, you cannot change. And in those cases, you have to use, existing hash, even though it gives you a bigger circuit. But if you're just designing everything from scratch, usually we recommend using, this series family of so-called ZK friendly hash. MIMC is one of those. Okay.
Understood.
Okay, and the last, we can just check, right? So whether it's a hit or miss, right? So of course, this is a ship where a ship it is, and that's why they are firing at. So you can easily do the math to see whether this is. I'm not going to jump into all the detail, but you can easily check. If you know the ship position, and then you are giving me this the coordinate you're firing, I'm going to calculate whether it's a hit or miss. Right? And the last final output is going to be, if any of your ship is hit, right, then I'm going to return, okay, this is hit. Otherwise, if none of this is hit, then I return false, right? So this is pretty much what the last line is. Make sense so far? So the public, so if you even can compare this with this diagram here, so you have all your firing, you have all your fleet position here, which is this, if you look at this, it has this private keyword. So in Socrates, when you declare the main arguments to be private, that means it's not only the prover can see this, the verifier The verifier is your opponent, right? The opponent give you, this, and you are going to tell him whether it's a hit or miss. And he's going to run the verifier pretty much. You can think of he's going to run the verifier to see whether it's a hit or miss. So by declaring this, as private, you're hiding the position of your location. But also, he can be confident you cannot cheat because you have this hash. You have to match first.
Mm.
Make sense so
Okay.
far?
Yeah. Just not
This is how
familiar with
this,
this.
yeah.
Go ahead.
Syntax. Yeah.
No, it's just that syntax with the little 2 dots there is a little new to me, but that's
Yeah,
out
this
of
one, I
scope, I
think,
guess.
yeah, this is like this is a little bit special, but otherwise, it's pretty much like a Python if you use any kind of Python code. Yeah.
Okay.
Any other questions here about the circuit? Anyone? That's good. Okay. If no other further question, I'm going to keep going. So the first step is, as I said, to design a ZK app is to design the circuit, because basically to see what is the function you are going to prove, and what's the inputs, what are the inputs, what are the output, and then within the inputs you're going to think about what inputs you're going to keep private. Basically your waitlist. You don't want to, if you want to hide from the verifier, what kind of inputs you want to use to declare as private in Socrates. I think here, because we don't want to choose sides, so in the existing zero knowledge community, there's quite a few different ways how you can do zero knowledge, and we just choose this. I think 2 most popular. One is called Socrates, the other one is called Circum. So because we don't want to choose side, we put the support for both. So if you want to use Socrates, you go to lesson 2. And but if you prefer Circum, we also got it covered. You can go to this one. But pretty much it's the same. It's just a different syntax. I think we're going to just give you a sense where you can just quickly come in and browse it. Same thing. It's you just encode everything, the ship position, and then you're firing it, and then you look at the hash, you compare it against it. So and in the end, you're going to see if any of the ship is hit, you're going to hit. Just syntax a little bit different, because this is more like a low-level language. You're pretty much actually programming the circuit. So it's like a gate. So you have signals input, you have signal output. So I think I'm not going to talk too much about Circum here. So if you want to know if you decide to choose Circum, you can also come here. So just on a high level, what's the difference between Socrates and Circum? So Socrates is someone like a more high level. It's like a Python. So if you're like just a developer, probably you are going to have, it's more developer friendly, I would say, to begin with. And Circum is like more like a low level language. You pretty much have to design, specify each gate. What does each gate do? So it's similar to like some kind of like hardware design language, HDLL. And the good thing is because you have low level control. So you can have, if you want to design some more, do more optimization, is if you know what you're doing, usually the circuit, but it's not always. Usually you can optimize the circuit to be very small compared to Socrates. And also some of the libraries, you can find some of the libraries in Circum, which you cannot find in Socrates, and vice versa. So yeah, it's really a personal, like a preference issue. So not a big difference. So you can choose whatever to use.
Okay.
Okay.
Would assembly be like a fair comparison with Circum?
I wouldn't say the assembly, because you look at the code, it's still, let's say, it kind of looks, you can still have, all the high level stuff, if else, you can have, declare variable, you can do the operation. It's just everything is like you are defining a gate. So you have the, when you have gates,
So
you have inputs, you have output. So you're literally wire the inputs and the output together.
okay.
So even from
So
the syntax.
okay. So maybe C then would probably be a little bit more fair.
Yeah, I would say a little bit C. Or for people who have heard about the hardware language, it's called HDL. That's a language that's used to design physical hardware, the circuit. And also, by the way, the author of this circum, because he's like an electrical engineer, so that's why probably why he designed it in this way, because he comes from that background. So think about this. Yeah, C. Yeah, I would say is yeah, you can think about that way. So one is Python, the other way is more like a low level C. I would say, yes.
Okay.
Yeah, you can look at the syntax of both and just choose whatever you prefer. And in the field, in the wild, people have been using both of this. I think a little bit more people using Circum because more libraries. For example, if you're doing a little bit of complicated stuff, let's say you're doing an elliptic curve. Let's say for people who heard about the Bitcoin, right, or the other kind of blockchain, usually they use the so-called elliptic curve based cryptography. So when you're doing elliptic curve in a circuit, if you add 2 points, if you're doing scalar multiplication, if you're deriving a public key from the private key, I think Circum has more such libraries. I think that's one of the reasons. If you're using, fancy cryptography, more complex, I think a lot of people, I see more people use Circum. But if you're just, staying not at the very cutting edge, you are just using some hash library. For example, MIMC, right? This one I just show you have the hash, but also Circum, you also have the hash. So it's not, unless you are pushing the boundary, I would say if you're just beginning, so for me, just my personal preference, I would just use Socrates because it's at least it's easier for me to get started.
Okay. Maybe
Okay.
the hackathon would well, that's another thing. Maybe that would be like a good thing to use.
Yeah. Yes, I
For
would
the
just.
hackathon.
Yeah, I would say if you're just getting started, you're not doing something very cutting edge. I think a Socrates is probably good enough for you. And then later on, for whatever reason you want to do proving more fancy statements, which I just talked about, right? For example, you leave a curve, or if you even want to verify some kind of signature within the circuit, you can check out Circum. And also, I think to talk a little bit, I think in terms of performance, because Snark.js, so this is the Socrates has 2 parts. One is the language itself. The other way is all the libraries. It's going to help you to do the setup, to do the proof generation, and also to get you how do you export to script verifier. So the prover in the browser can be a little bit, Socrates is a little bit slower. So that's just another performance issue, but not too slow, I would say. In the last step, I think I'm going to compare a little bit when we talk about the last step again.
Cool.
Okay, anything else? If not, we can just keep going. So after you have designed the circuits, the next step, of course, if you want to put on chain, of course, you are going to come into, the smart contract development phase. And before everything else, you're going to, because in the smart contract, one thing you must do is to integrate zero knowledge is to integrate the verifier, right? How do you get the verifier? Basically, you can run this command line. If you're using Socrates, you can run this line. What does this do? I think briefly, I've talked before. Basically, it give you the verifier in script in a library. So you can import this library into your smart contract. Then in your smart contract, you can verify the proof. So this pretty much, you can think about this as a library. You don't have to know it's auto-generated. So you can almost always find this. You have to, whatever your contract you have, you're going to import this auto-generated verifier contract. And this is generated from the tools we have. You can either have the Socrates, or you can use Circon together with Snark.js. It's going to give you the verifier. I think this is basically the high level code. You can see from here. You can just put your inputs. So in a verifier, you can, if you still remember, right? So you have two things, actually three things. You have the public inputs, you have a proof, and also you have your verification key. But this one is already hard coded, so you don't have to worry about this. So when you call your function, you only have to give out two things, the proof itself and also the public input. So you're going to tell you whether this proof is valid or not. It's going to return. But you can treat this as like pretty much like a magic black box. You put this thing in, and you are going to guarantee this one is going to, if it's good, you're going to have return true. Otherwise, you're going to return false. Does this make sense so far?
Yeah. This was, I think, covered in one of our previous classes last week. I think we were talking about this.
Yeah, this is more like a concrete instantiation of that. So once we have this verified, the other part of the smart contract is not very different from, just let's say non-ZK based smart contract. So for people who have are kind of familiar with, script development, you probably know. If you're not, so this is lesson 2. So just for people who is watching, who are not very familiar with script. So if you want to just know a little bit more, the basics, this is lesson 2. Think about this a little bit more advanced. So if you want to, how to integrate the code with the smart contract code and how to program it, you definitely can check out this one first. But if you're already familiar with script, so this should not surprise you here too much. So basically, you're going to have a smart contract at the highest level, and then you're going to, have your public key and your opponent's public key. So basically, it's almost like an identifier, right? And then you're going to commit to a hash. This is the position of the hash. So when you first deploy it, you already commit to the hash. So you cannot change it later. So the hash is going to be a property for the contract. And then something can change because it's a turn-based, right? So you move first, and then your opponent move, and then you move again until somebody loses. So you're going to have some kind of mutable state. So not surprisingly, you can use the state decorator based on whatever you put in here. It's going to be a mutable state. You're going to keep updating the UTXO. So you have a chain of transactions. That's how script simulates. For people who know script, that's how we simulate state. And also there's a variable to say whose turn it is, right? Whether it's your turn or your opponent's turn. So the rest is pretty much standard, state for smart contract. If you look at the tic-tac-toe example, you're probably not surprised. So basically you can have this is the non-state variables, and this is the state variables. It's going to count, how many times you have to hit. So the only major difference is what I hinted earlier. You are going to have ZK Snark verifier. Going to verify, when you have this proof. Let me see. Oh, sorry. It's just too sensitive. So you're going to verify the proof, because every time you're going to move, right? So you're going to fire at the position, and it's going to the opponent's going to generate proof saying whether it's a hit or not, together with the proof, because you don't want to trust your opponent, right? Because it's a kind of adversarial game. You don't want to just take his word at face value. You want to verify it. So you can use the ZK snark, the previous verifier, auto-generated verifier counter to verify this. So that's that's pretty much the only difference. Basically, you have to auto-generate this contract. Once you import it, you can use this. This is a library. You can verify the proof. So once you have the proof, everything else follows like a regular, script contract development. So here, I think another thing is you have this state, right? So it's what you have three. Yeah, pretty much then you have two outcomes after each move, right? Because one is, what if one of the players, the whole entire fleet has been sunk, right? Then that's end of the game, right? So because this is like a competitive game, so before everybody starts, each of them has to deposit some kind of like a stake, right? Let's say we play this game, each of us put 1 Bitcoin in. So at the end, pretty much this says, hey, we know who the winner is. So all the money is going to go to the winner's address. So if not, this is the final stage. If not, we just keep going. So this is pretty much what the code here does.
Capiche.
Okay. So I think this is not the most complex part. So I'm not, if you already know it's script, so you should have no problem understanding this. It's very similar to tic-tac-toe. The only major difference, as I said, is you cannot trust your opponent. You have to verify, whether the firing you just fired at the coordinate is a hit or not. He's going to tell you, and you cannot trust him. So you use the expert verifier to check it. But that's the only big difference in terms of whether it's ZK based smart contract or not. Any other question? Here?
So is this comment right here? This comment is for us to add code so that we can call.
Oh yeah.
Okay.
Yeah.
Okay.
So
I understand.
because this is interactive, so we don't want to just, because
Right.
we want to practice on. So you can try it after you finish. You can also check the real answer and just to see whether you got it right.
Okay.
But in most cases, I would say almost all the cases, don't mess with this. Don't change any part of this code. This is auto-generated. That's like any other auto-generated code. Maybe I should put some big, exclamation marks here. Do not modify this code. So this auto-generated in most cases, unless you're doing something very advanced. This one, don't change this code. You can pretty much just ask after you export it, you can just import it and then just call this verified code. Don't change any code here.
Cool.
Okay. So if no further question, let's keep going. So we talk about, the step 1 is to design the circuit. Step 2 is to design the contract, right? And then the last step, this, if you're just learning, I think most people just stop here. But if you really want to build a full functional app, right, that's not enough, right? Because, now I can interact with the app, with a smart contract, I can deploy it onto the blockchain, right? I can also interact with it. I can send it some proof. It can tell me whether it's good or not. But then the end users, they have to have a way to interact with this without, knowing all the details. So that's why usually you add some kind of a web front end, right? So that's what we are doing here. And eventually it's going to look like this, but you can also get a sense what it looks like by. So before we go into into detail, the front end, this is what it looks like eventually. And you also need to, install some kind of wallet. For our case, we recommend you use a Sensilit, but there's some other wallet you can use. So for people who have not heard about the Sensilit wallet, it's a Chrome extension. It's pretty much like a MetaMask, but for Bitcoin, it's not for Ethereum. So it's called Sensate. So you can download it. You can also get some test coins from, some faucet. So once you get some faucet, then you are ready to go. So this is the prerequisite. And also, we also, have an online version here. We build this. If you can click, this is what it looks like. And it's not just we're saying it. You can actually log in and actually play with it. So this is what it looks like eventually. So once you have the wallet set up, you already clone our app. You can then go to the next step. It's going to walk you through, how do you, so again, you have two choices, right? If you're using Socrates, you're going to use the Socrates library called Socrates-JS. You're going to install that. If you, npm install if you're already using TypeScript or just vanilla JavaScript, you just use the same tool. Once you import Socrates JavaScript, you can do all the, the zero knowledge steps we have been talking about. Basically, you can do the whole workflow. You can compile it. Previously we just showed you how to use Socrates CLI, right? Command line. Basically here, you're pretty much doing everything. You can also through the Socrates JavaScript API. Does this make sense here?
Yeah. So yeah, as soon as you install it, you're able to do those. Yeah, it makes sense.
Okay, the workflow. Yeah, just not doing. You're not running the CLI to do it. Yeah, you can do it in JavaScript. Pretty much it's the same with the CLI. So you can check out more the documentation on how to run this. But also we put, because for us, we also put a wrapper on top of it called a ZK provider. So then you can expose all this interface. So you can have init, basically, pretty much you get all the setup ready and compile it. And then every time, how do you trigger it? Basically you fire, right? So how we also put, the code to see where it is put. So it's going to, you can pretty much readable here, which is, you can compute the waitlist and then you can generate the proof. And then even when you have the proof, you can also verify it. Just, you can verify it in the contract, but also, even before you send the transaction, you also want to, you can also locally verify it, because if it fails locally, you are not going to succeed in the contract. So you can save some fees. You can try it locally here. So pretty much just what you can do using the CLI. Now you can do it in the code. Okay. So this is pretty much the normal, zero knowledge workflow. You can compute a waitlist and then you can generate the proof. And then once you have generated proof, you can also verify the proof also. So for Socrates, you use the Socrates JavaScript library. Make sense so far? To deal with all the ZK related code.
Now, when you say CRA, is that the environment? Because I'm not familiar with that terminology. Okay.
Oh, the command line, basically. So let's say, what's the example? So if you still remember, create the first. So I think one of the previous session where I talked about this, so you can download the Socrates, the binary. Once you have this is the command line. Basically, you can run the CLI. This is the command line. I mean, you can type in your command line, input, and you can do everything here. Compile, set up, compute waitlist, generate proof. If you look at this, this is exactly happening here, right? So basically, you can also do all the steps, but in JavaScript code, not using the typing some kind of command, prompt.
Understood.
So do the same thing, but in JavaScript code. Yeah.
Okay. And does that stand for computer? I'm looking it up online right now. but I don't think that's what it means. I'm getting computer research infrastructure. That's
CRI,
CRI.
CRI, yeah, it pretty much means command line in
Okay.
in coder's word. Yeah, I think it's command line interface. Pretty much just command.
Okay.
It means command. Yes, it means command.
Okay. Okay. Yeah. Command line interface. Got it. CLI.
Yes.
Okay.
Yes.
Got it.
Okay. Yeah. Basically, I'm saying is this Socrates-JS is the same thing as the equivalent of the what you type in the CLI command. You can do all the steps, but in JavaScript.
Understood.
Can you speak about the speed of the gameplay and why it's kind of slow? Is
great.
that because it's doing all of those steps?
Yes, it's great. Great question. I think that's you almost read my mind because that's what I'm going to talk next. So you see there's a section here. So I think as I hinted before, the bottleneck for most today's ZK Snark system is when you generate a proof, it can take a lot of time and a lot of memory. And because we are doing in a browser environment, browser JavaScript, it's not the most performance computing, the language or the running runtime, right? Because, for example, you can do some kind of a graphics processing, right? Usually you do it on a locally, not in a browser. Browser is not, at least for now, it's not intended for high performance or very computationally intensive application. So it's a single thread and it runs slow. So that's why when you generate a proof, it's going to can take you tens of seconds, because just the proof itself is, the big N, right? It's going to be quadrillion. It's the most expensive part. So it can take you up to 10 seconds. So that's why sometimes when you click, it may take a while for you to generate the proof. The verification is like just some milliseconds. It's going to be, super fast. That's not the bottleneck. Bottleneck is generate the proof. Okay? So to handle that kind of I would say long delay, one typical trick you can play in the JavaScript code or the web code is, instead of doing in the main thread, you launch another thread, so-called worker thread. So it's almost like a multi-thread, but within the browser. So from the UI, you never get freeze. So you can click, and then you instantly click play again. And then in the background, the worker thread is going to do the hard work, do the heavy lifting of producing the proof, but in the background. So that's how you usually, if you ever find your approval time is too long in the browser, that's adversely affecting your user experience. That's one trick, a typical trick you do. You put the proof generation in another thread. So you can, in the UI, the user never experience a delay. It's pretty much real time. And then the background, the worker is going to producing the proof.
Are you referring to multi-threading? Is that what you're referring to?
Yes, multi-thread in JavaScript browser. Does this make sense, Dave? But only do this. Only do this if it is an issue, because it all depends, right? Which library you are using, and also, how big is the circuit. So if first version, I would suggest just don't use this. Just see how fast you get. But if ever a bottleneck, you can use this approach. So it becomes async, right? So when you click, you're going to submit to almost like another thread. So you don't wait for the proof to be generated, just keep going. And then another thread just keep computing in the background. So in this way, the UI is always responsive. You never say you click and then you have to wait for 10 seconds for it to click again, right? It usually depends on what kind of apps you're building. For this, right, it's supposed to be real time. So that's why we're putting a worker. And then in this case, I don't know, have you played recently? Because we kind of upgraded. You usually take like no more than a couple of seconds. At the first version, we are not doing any optimization, so sometimes it take like 10 seconds. Right now, is less than a couple seconds. But if not, let us know.
If I remember, it was taking more than 10 seconds, but I'll try that with the new code.
Okay, and also remember, it also depends on your computer right? And network, everything, because you may have like 100 tabs open. It's probably going to be slow. If you're dealing with a very slow computer, yeah. So it depends on a lot of factors, like any other kind of web apps. So if you ever feel is too slow, use this trick. Okay.
Okay, and this has to do with the CMI. I think it was, what was it referred to? CMMI algorithm. CRI. No, sorry. No.
The prover time.
You were saying that you were using an alternative to SHA-256. You're using something else.
Oh,
I think
MIMC. That's
MIMC.
related. Yeah, basically the shorter the smaller circuit is, the faster it's going to be to generate the proof. So that's another reason, right? You want to keep the circuit size as small as possible, because if you can even do some, you can use this example to try is to switch out the hash part instead of using MIMC. For example, you can switch to SHA-256. I think you are going to instead have a couple seconds. You can probably have maybe like I would guess like 10 times. Let's say 30 seconds. You can try. Then you can notice, oh, why do we use some kind of like a special hash for this? Not just let's say SHA-256 or SHA-3 even.
Okay.
You can even play with it. You can switch it out. You can notice it become noticeably slower.
Okay, but the question I was trying to ask was, is that the principal reason why it takes that long, like more than 10 seconds with what Dave was asking, because of the algorithm that you're using?
Not the algorithm, but basically, okay, here's the thing. It doesn't matter much like what specific algorithm. The prover is usually is quite slow. Is the slowest part. So that's what I'm saying, right? So if you even use MIMC, so-called ZK friendly hash, probably going to take you a couple seconds. And if you switch it out, that part, it can take you to tens of seconds. But it's very hard to, right now, especially in browser, it's very hard to get it to, like, let's say, almost like an instantaneous, because that's just the nature of the beast. That's the bottleneck, because it's going to be even in the big O(n), right? It's going to be all n log n. So if the circuit is a little bit big, you're going to take quite a while to generate the proof.
Understood. So it's the zero knowledge proof that's taking the most amount of time, not so much the
Yes.
hash algorithm.
No. It just generate the proof. That's usually the bottleneck.
Understood.
Okay. So I think that's pretty much the end of it. I think I'm going to, if you want to just go back again, okay, let's go back to this one. So we just talk about, how to hook up with the UI and how to generate the proof, right? So we're talking about using Socrates-JS, but again, you can also using Circom with this library SnackJS. I think, yeah, our experience so far is that SnackJS is a little bit more performant. Maybe you take 1 second instead of 2 seconds to generate the proof for the zkBattleship. So that's another reason, maybe some people can prefer to use Circom and SnackJS, but not huge difference though. In this small example, maybe you go to much bigger circuit, you may have a much bigger difference. So at the last step, of course, now you have the circuit. You can generate the proof in your JavaScript code in the browser. You can then hook up with this. Now you have the contract, right? So you're going to use again. This is standard script contract code. You can use our JavaScript code to integrate with your app. So you can do deploy. You can do call the different functions of the of the contract. So this is pretty much, I would say, it has nothing to do with the ZK part. So I'm going to just skip this part. This is pretty much just standard script, integration code. You can compile it, and then you can deploy the contract, and then you can call it. But also when you call it, you have to pass in the proof, right? And the proof is generated with, let's say, zkBattleship-js code. So that's how everything hook up together. So to deal with the circuit, you use zkBattleship-js to, integrate the contract itself with the web app. You're using, script SDK. In this case, it's scriptlib. Okay. So that's the end. I think we just go through. Let's, even go to a little bit high level, see what we have covered today. So we have covered, from the beginning, we first designed the circuit, and then we designed the smart contract, and then we use, the SDKs, from the circuit and also from script contract to together hook up with the front end code, which in our case, of course, we haven't covered, but is we use some UI from we just fork another repo from somebody else. We don't want to design the whole front end. So that's one option for you too. If you are in the hackathon and you are not quite a UI person, that's another trick. You get some open source code, and then if they already have some kind of UI, you can pretty much reuse that can hopefully save you some time, because most of the time you're probably going to have is design the circuit and the contract. Just something, maybe you can think about. You don't have to design from scratch if you're not like a front end person. Okay, any final thoughts?
Nope.
No? Okay. Okay, then that's good. I mean, we covered the whole workflow. So hopefully anybody who's watching this, we are launching our hackathon. I'm going to again post the registration link in the show notes. So definitely register, and I'm going to look forward to see what kind of ZK apps you guys can build. All right. Thanks for coming. Hope to see you next week.
Thank you.
Okay. Have a good day. Okay, everybody, and a good weekend. Okay, bye-bye.
You too.
Dave,
Bye-bye.
Jay, and Michael, bye-bye. Oh, Zach already
care.
left. Okay, bye-bye.
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 And thanks again.
Okay, thank you.